this is from yesterday. Yesterday we have an Anzac Day, so we are not able to take a weekend lecture. So I move weekend lectures here in these mornings. I found your timetable is empty today morning, so just just to give you overview of week 8. After completing these lectures, you can take questions too in your assignments. And very important week that we're going to start now, which is the force methods. Week number 8, the name is force methods. That's we're going to use to analyze the indeterminate structures that I'm going to give you some more insight. Now, as you know, energy methods that we have taken in week number 7. Now, in energy methods, we have taken the two concepts: external work done and strain energy. If you remember, external work done 1/2 P delta. If you have a bar, and if you have applying the load, and if you have deflections, and if you're increasing the deflections, the area under this curve, which is a triangle, is 1/2 V delta, and strain energy is 1/2 stress times strains. And then you can have a external work done equal to internal work done, and you can calculate the force. But this method has a limitations that it can only use when you are applying the load at that point where the load is applied. That's the deflections where you find. But on the other hand, principle of virtual work is a very powerful method. It can be used for finding the deflection in the truss, beams, frames, and it's very simple equations. As you know, we can just apply the virtual load where you want to find the displacement and find all the internal forces. We find the internal forces on the real structures, which is capital N, L, and EA, and you substitute the value, you will get these displacements. Similarly, for the beam, you can find the capital M, which is the internal moments for your beam. And then you just apply the virtual load or virtual moment, depending on if you are finding the deflection or rotations, you can calculate the internal moments. Very simple methods, and based on these methods, you can take questions 1 in your assignment 2. There is a very simple beam questions that you can take it. Hopefully, if you work every week on questions on that topic, you will able to finish the assignment very smoothly. Now here we are in the week number 8, almost approaching the end of the semesters slowly. More than 50% topic have been finished. Now, these new topics that you are going to learn here from week 8, week 9, and week 10, they are different than the previous 7 weeks. What is the main difference? That in the first 7 weeks, you have given the structure which is a determinant. Determinant meaning that, let's say you have given the simply supported beam, or you have given the cantilever beam, where your unknown is 3 unknowns. Let's say you have 3 unknown reaction forces. For example, here as well, you have 3 unknown reaction forces, and you have 3 equilibrium equations, meaning that sum of the force in the x direction equal to 0, sum of the force in the y direction equal to 0, sum of the moment equal to 0. There are 3 equilibrium equation, 3 unknown, meaning mathematically you can find these 3 unknown values, because if you want to find the unknown values, you need the respective equilibrium equations. So from week 1 to week 7, the topic was simple. It was a determinant beam, determinant truss, where you have equilibrium equations and unknown values are same, so doable. Now from week number 8, we are going to talk about additional indeterminacy, meaning that you have additional unknown forces. Let's say I put 1 roller here. For examples, I put 1 roller because it was deflecting. This beam is deflecting too much, so I put the extra roller. So if I put extra roller, I have extra unknown force. So if someone asks you to draw the bending moment diagram, shear force diagram for this beam, you may not be able to use all these methods that you have learned in the previous weeks, right? You understand that, right? You have this reaction force, you have this reaction force. You apply all these equilibrium equations, but you will not be able to find all four unknown forces. You can try, you will not be able to find because you have two equilibrium equation and four unknown values. In that case, these force methods will be useful. That force methods will allow us to find the reaction forces, additional reaction forces, and once you find the reaction forces, you can draw the shear force diagram and bending moment diagram. Now, our ultimate goal, most of the ultimate goal in structure analysis subjects, you will ask to either draw the shear force diagram, bending moment diagram, or deflections. That is the outcome of the structure analysis subjects. There is nothing else, right? You're not going to learn any additional quantities. There are various methods that there are various approach to get that answers, right? So here in structure analysis, deflections, shear force, bending moment diagrams, those are the. So let's start on the force methods. As I mentioned, these force methods, these lectures will introduce the force methods to analyze the indeterminate structures. As I mentioned, what is indeterminate structures? Indeterminate structures are the structures where your reaction forces, let's say you have one reaction, second reaction, three reaction, because you have fixed support and this is roller support. So four reaction forces, number one, number two, number three, and number four. You have four reaction forces unknown value. And you have three equilibrium equations. Sum of the force in the x direction equal to 0. Sum of the force in the y direction equal to 0. Sum of the moment equal to 0. Now you have those three unknown, three equilibrium equations, and you have four unknowns. So we can't use our conventional methods, equilibrium equation methods to solve those unknowns. So now we are going to introduce these force methods to find this extra quantity, extra fourth one. How we do it? This is the methods. Very simple pictures given to you, but I will show it to you. I will explain you that in slowly. So you have a. If you need more information, you can find it in the chapter number 10 of that book. And I think this book is available online from our library. And I think link is given in week number 1 lectures. After completing this week force methods, you can take questions number 2 in the assignment number 2. Okay, very simple. So every week we have a topic to cover. Force methods, some quick introductions, how the methods works. Then I will give you the step-by-step procedures to solve these examples. Then we will take an examples based on these force methods for the beam and truss. And then finally we will summarize in the 2 hours times. So let's introduce these methods. Determinant structures and degree of indeterminacy. Before moving on to the actual methods, let me give you some vocabulary. Vocabulary means there are some terminology that are introduced new here, and I will explain you that very slowly. Now, a structure is indeterminate when the number of equilibrium equation is less than the number of unknown value. As I mentioned, right? Number of equilibrium equation, how many? Sum of the forces in the x direction, sum of the forces in y direction, sum of the moment equal to 0. So there are 3 equilibrium equations. Is less than the number of unknown. For examples, as I mentioned in our previous examples, we have number of unknowns. Unknown number 1, unknown number 2, unknown number 3, unknown number 4. So you have 4 unknown. So always when your equilibrium equation is less than number of unknown, or you can say on the other one, unknown values are more than equilibrium equation, then these structures become indeterminate. That is the name of that structures. The structures can be classified into 2 categories. One category, determinant structures, simple. Week 1 to week 7, when you have number of equilibrium equation is equal to number of unknown values, you can call them determinant structures. Like mechanics of solid, whole subjects in year 1 is talking about determinant structure. Now this is new, indeterminate structures where you have extra unknown values. That is more than the equilibrium equations. Most structures in the reality are indeterminate. You have not seen the beam is just like this. Right? You will not come across this kind of a simple beam where you have just the pin supports and roller supports. If you are driving the car on the bridge, there are additional columns that carry that beam or that beam bridge beam. If you go in the buildings, there are multiple columns that's supporting the beam, right? So you can see these are the supports. Right, so in the reality, all the structures are indeterminate, right? You will not come across these determinant structures. Then someone might ask, why do you teach us determinant structures? Look, the determinant structure is very fundamental. It's very is give you the explanation how the theory works. And once the students understand the theory and fundamentals and foundation of the theory with that easy concept, it is good for students to absorb that indeterminate structure. So now all the structures that you come across in your real life, in your career as a structural engineers, you are going to analyze the indeterminate structures. Now, for that, degree of indeterminacy, or we call it number of redundancy. That's the new terminology that I'm introducing it right now. Degree of indeterminacy or number of redundancy. They both are interchangeable words. You can call them degree of indeterminacy and number of redundancy, and that is represented by capital D. Is the difference between the number of unknown and equilibrium equations. Basically, that D is telling me how many extra reaction forces you have, which are more than equilibrium equation. Here, degree of indeterminacy is 1. This structure is classified as a indeterminate structure with degree of indeterminacy equal to 1. What does it 1 represent? That there is an extra 1 unknown value presence in the structures, which is more than the equilibrium equation. So D will tell you how much extra quantity that you are dealing with, right? So that is the number of unknown value, which is here is 4. Take away number of equilibrium equations, which is 3. So degree of indeterminacy is 1. Very simple, right? It's not that difficult, right? There is an equation as well. You don't need to remember these equations, but I think I will practice with you the equilibrium equations. So when you are talking about the truss, and if you want to find the degree of indeterminacy for the truss, this is an equation. Degree of indeterminacy is equal to m plus r minus 2n. M is a number of members, r is a number of reaction force, and n is a number of nodes or number of joints. Okay, we will take an examples that will give you more insight of this equation. So, but you can just introduce yourself m plus r minus 2n. And for the beam, if you want to find the degree of indeterminacy D, you have 3m plus r minus 3n, where m is the number of members, r is a reaction force, and n is a number of joints, right? So let's take an examples on that one. I will do one and then you help me for the rest of this one. Now this is a truss and someone asks you, can you please find me the D? D equal to how much? Which is degree of indeterminacy. Determine a degree of indeterminacy. So for that case, we have an equations to calculate the degree of indeterminacy here. Equal to this m plus r minus 2n. How many members? You have member 1, member 2, member 3, member 4, member 5, and member 6. Then member 7, member 8, member 9, member 10. Right? So in this truss, you have 10 members. Let's put 10 there. Right? I hope I did not make any mistakes there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 members are there. How many reaction force? Reaction force number 1, reaction force number 2, reaction force number 3, reaction force number 4, right? Because pins support has a 2 reaction force. So there are 4 reaction force. Take away 2. These 2. How many joints? Joint number 1, joint number 2, joint number 3, joint number 4, joint number 5, joint number 6. Am I missing any? 1, 2, 3, 4, 5, 6. I think there are no missing, so 6. So that is 14. Take away 12. Degree of indeterminacy equal to 2. As you can see, these structures you can't solve it with the equilibrium equations because there are two extra quantities. There are two extra unknown quantity which are more than the equilibrium equation. So degree of indeterminacy for this truss equal to 2. Right? Do you understand this truss? If someone asks you to find the degree of indeterminacy in the truss, you can use these simple equations, plug and chug, and you get the answers. And someone asks you what is the meaning of that number. I don't want you to just put the values and you get the answers and you will just not understand them and the theory. The degree of indeterminacy meaning that there is an extra two quantities that you are dealing with, right? Now let's take an example for beam. Now let's take an example for beam. And someone asks you to find a degree of indeterminacy for this beam. Now for this beam, we're going to use these equations. D equal to 3m plus R minus 3m. What would be the m? Is 1 and 2. Someone might ask, how come there are two members? Because there is only one beam. Now, when you have a beam like this, and they are the columns like this, they are columns. So this is one member, this is second member, third member, and fourth member. So it's a one beam, but within that one beam you have a member. So you can easily recognize between the two supports, between that you have one member and second member. So you have two members. How many reaction force? You have one reaction force, you have two reaction force, 3 and 4. So you have 4 reaction force. 3 times n. How many joints? You got one joint, you got second joint, you got 3 joints. 3. So 6 plus 4 minus 9, 10 minus 9 equal to 1. Right? So that's good. No problem, right? Degree of indeterminacy equal to 1, meaning that this beam has a one extra quantity. Now, students, can you please perform this degree of indeterminacy on this beam and tell me what is your answers? Okay, if you don't want to talk, you can just put your answers in your chat. In your chat, just a numbers. What would be the degree of indeterminacy for this beam that I just circled? It's possible to do it. Let's give you a couple of minutes. And can you please find the degree of indeterminacy for this beam that I just circled? You can say the answers or you can put in the chat. This beam. All right, now let's check. We're going to use this equation, D equal to 3m plus R minus 3n. Okay, how many members? You got member 1, member 2. So 3 times 2. How many reactions? 3 reaction here, 1 reaction here, 4 and 2 reaction here. So 4 and 6. So 6 reaction. How many joints? Joint number 1, joint number 2, joint number 3. So 6 plus 6 minus 9, 12 minus 9, 3. If you both get the same answers, I will not going to show you the calculation because I think you know the concept, but just do the last one. And if you both get the same answers, I will accept it. If you get the different answers, I don't know the answers, by the way. To be honest with you, I don't know the answers. So if you get the separate answers, I need to go for the calculations. If you get the same answers, we will accept this one as a 7. So should be fine. Let me know if you have any questions or if you don't get this concept clear. Now, very simple idea how this gonna degree of indeterminacy, you know now. So for indeterminate structures, we use equilibrium equation is not sufficient. Now you know that there are 3 equilibrium equations, 4 unknown values. So the equilibrium equations are not going to help us in the overall process. It will going to help because there are 3 equilibrium equations. Of course, we're going to use them somehow, but they are overall not going to helpful in the full in to get the final answers. Therefore, idea of the force methods to use additional compatibility conditions. So we need additional equations that is called compatibility condition. That is a new word for you. Don't worry about it. I will tell you what is compatibility conditions. I hope you understand indeterminate structures. Now let me help you with the compatibility condition to solve the redundant unknown force. So now you have three equilibrium equations that you keep it with you. That is no any issue for that. We don't want to forget that. We will keep it that with her. But there is an extra quantity. Let's say degree of indeterminacy is 1. So you need extra 1 compatibility conditions. If you have a degree of indeterminacy equal to 2, you need 2 additional compatibility conditions. So you have an extra equations that will help you to solve those unknown forces, unknown redundant forces, right? So that is the helpful, right? That you have three equilibrium equation plus additional compatibility condition. How many compatibility conditions you will get depending on how many degree of indeterminacy you have. So in these methods, we have to create primary determinant structures from the real one by removing the redundant and reaction for internal member forces. So let me help you this one. So this one, can you please find the degree of indeterminacy in this beam? Can you please find the degree of indeterminacy for this beam? Please find degree of indeterminacy on this beam. You have equations or you have the methods that you use in the previous example. Equal to 1 in this case. Now, if you have 1, that means you need to remove that 1 because you are telling me that you have one reaction force here, another one here, another one here. So you have an extra quantity. So you remove that extra supports. You remove these supports. If I remove these supports, then this becomes the determinant structure. So first job is to make the structure determinant. How are you going to make the structure determinant? First, you find the degree of indeterminacy. From that degree of determinacy, you will know how many reaction force you can remove from the beam that will help you to make the structure determinant. So these structures is the determinant structures. As you can see, 1, 2, and 3 unknown forces, 3 equilibrium equations, perfectly fine. But here we remove something, so there is an extra force that you just need to put as a CY. We don't know. There is an additional force that is there, that is CY. Now, what is this force? There is this force here that will, because when I remove these supports, before this beam will have this kind of a deflections. Do you agree with me? That is the deflection shape for this beam. But when I remove this one, when I remove these supports, I might get like this, right? There is a deflections that you get at the delta C because of when I remove that supports in the primary structures, you will get this deflection. But then I put extra force that will push back these to here, right? That I put the extra force to make it 0 because at the moment here deflection is 0. So I put additional CY to put the deflection 0. So in that case, CY equal to that we need to find that deflection equal to 0. So this is your primary structures. This is called primary structure. What is primary structure? Primary structures, by the way, is a determinant structures coming from your real structures by removing the redundant force. How many by removing the supports? There is no rules which one you're going to remove. There is no rules that which part. You can remove this one as well. As you can see, if I remove this one, then there is an additional force By that will make that one 0. And that is C. Now there is a one condition though here that you make sure that when you make a primary structures, you will make that stable structures. Do you remember that in your space gas software, you will get the error called instability? You don't want to make this structure instables. Instables meaning, let's say someone will come back and say that, oh, you want to make a determinant structures, let's make this one roller. This roller, this roller, this roller. Let's make not remove these two supports, but let's make this one as a roller. Then this is become a skateboard, you know, Beam cannot be a skateboard, it's just moving. So this is become unstable structure, unstable. Right? So keep in mind that when you make your structures determinants, when you remove the redundant force, you're making sure that these structures are the stable structures. So that's the one rules that you need to follow. How to create the primary structures? As I mentioned, you can just remove them. If I find the degree of indeterminacy here, it would be 1 here. Based on 1, you can remove 1 extra supports because you have 1 reaction force, second reaction force here. So you can remove it, 1 additional force, and you put the CY. Or you can make these fixed supports to the pin supports, because when you make these pin supports, this reaction force become your redundant moment, right? So you can make the pin supports become roller supports. Make sure that is a stable structures. The fixed supports can become the pin supports, and roller supports you can remove it completely, right? So because you have 2 reaction force here, it become 1 reaction. Here you have 3 reaction force, it's become 2 reaction force. I hope you understand that is 0. So if you have a fixed supports in the real structures, you can make a pin supports in the primary structures. So this is primary, this is real, because here you have 1, 2, and 3. So you are 1 and 2. If you have a pin supports in the real, then you make it roller, and that is primary. And if you have a roller here in the real structures, you can make it just nothing, free. Let it make it free in the primary structures. So I hope you understand that how you make the primary structures. How many unknown reaction force you remove depending on how many degree of indeterminacy you have. All right, before moving on to this one, give you the procedure. Don't worry if you don't get the full concept on the procedures, because when we take an examples, you will get more understanding on this matter. First, we're going to find a degree of indeterminacy. And you know how to find a degree of indeterminacy by now, because we have taken a couple of examples how to find a degree of indeterminacy for truss and beam. Then you create the primary structures. And by the way, primary structures are the determinant structures. Do you understand that? Primary structures meaning you remove, you make a cantilever into pin supports into roller remove completely, and then you do something. How many you gonna remove depending on how many degree of indeterminacy you have. And then you calculate the displacements. Where are you going to find the displacements? If you remember that in the last examples that you have this roller here, and then you have fixed supports, and you make the primary structures by removing this roller, then you need to find the displacements at this particular point. As I mentioned, the displacements, because when you remove that supports, it will deflect. So you need to find that displacements. And then you need to calculate again the displacement in the primary structure due to redundant force. So then there is another structures that you can make it and find the deflections. There are 2 deflections that you need to find. Look, these methods that we're going to teach you is very simple. If you know the virtual work methods, there are 2 examples, virtual work example in 1 examples, because it's just finding the displacement. Others are very simple. If you know how to find the displacements in the beam using the virtual work methods, week number 7, these methods is easy peasy. There is no any big things. Of course, I introduced few concepts there, but once I take an examples, if you know the displacements, you can do the force methods like this and apply the compatibility equations to solve the redundant force that I'm going to show you in the examples. Now let's take an example here. So how am I going to, because first you find a degree of indeterminacy equal to 1 here. That is step number 1. Job done, easy. Find the degree of indeterminacy, step number 1. Then make up primary structures by removing 1 force. So let's make this roller redundant force. So when I remove that roller, these structures basically have this displacement shape. But when I remove it, it will have these displacements that you're going to find using the virtual work method. So find this displacement delta B. Then because then you remove everything and you put this one there. I can explain you why I put the one and so on. So as I mentioned, this when I remove these ones, this is not actually the real case, right? Because here we have a support. So I need something. I need some force that can push this point back to point B, right? That make it 0, of course. OK, but I don't know what is this force, right? Because I hope you understand. Let me turn on my, because when you don't know, let's give it the go. Let's put one. Don't worry about it. Just put one there. OK, if you don't know, let's put one. So when you have one, then you have FBB. FBB is called flexibility coefficient. What is FBB? If you don't remember any of this name, don't worry. But as a part of the theory, I'm just explaining that when I have a one force, then there is a displacement called flexibility coefficient FBB, and B is the force applied at point B and the displacement at B. So that's simple, right? So I will explain you that BB when we have another examples. So now, as I mentioned, I don't know what is the force, but I know there is a reaction force By. So if I multiply 1 by By, then this displacement should be multiplied by Y as well. Like for examples, if I have a 1, then the displacement is 2. When I have a load 2, displacement is 4, because it's the elastic region. Is the elastic regions, meaning that this beam is in elasticity. So it's a linear relationship between the force and displacement. So when I have a force 1, you have FBB. When I have a force By, which is 1 times By, then your flexibility coefficient also multiply by By. I hope you understand that. The same way, like if you have 1, displacement is, let's say, 2. If you have a force 2, displacement is 4. If you have force 3, displacement is 6. So it's linearly increasing with the displacement. So in that case, my final one become By, and then this displacement become By and Fy. Now, once you know that, then you have a compatibility conditions. What is compatibility condition or compatibility equation? Compatibility equation saying that this delta B, which is going down due to removing that force, is equal to this force going, this displacement going up, right? Because you know that whatever the force that you have coming down is equal to this force, right? Then it will become 0, because the displacement here at this point is 0. Displacement delta B equal to 0. So this delta B, which is this one, plus this is, let's say, down. So it's minus, this is up, By FBB equal to 0, because that is delta dash BB equal to 0. So in that one, if you know this one, you can calculate By. Right, so that is an additional compatibility conditions that I introduce here to find those By. Once you know the By, then you can easily find other unknown quantity. There is another way as well. This is one way. There is no rules, by the way, that which one you're going to choose. The easier one that I show it to you. The students may find difficulties here, that you can make this one. You can keep this roller, and you can make this this one as a redundant, this moment. So this fixed support become pin. For that, your moment is redundant. Then you have rotations, because here there is no rotation, by the way, here when it's fixed. But when you remove that fixed supports and make it pin, then it's rotate. So this rotation you need to find, and then you put it back, these moments back, and you have one moment, and then you find this rotation, and you can find MA. Same concept, same like that I explain you here, but it's the concept of moment and rotation, here force and displacements. Okay, these methods will get really complicated when you are going to use these methods for degree of indeterminacy greater than 1. Degree of greater than 1 means degree of, let's say, degree of indeterminacy 2. It will become really challenging. Really challenging means mathematically it will be, if you are going for degree of indeterminacy 3, 4, then it will be really long. For that case, next week is a surprise. Next week we have a slope deflection matter. So if your degree of indeterminacy is more than 1, then I encourage you to use the slope deflection methods. Degree of determinacy equal to 1. OK, manageable. But when the degree of indeterminacy 2, then you will find challenging. You will see how. So here, let's say you have these examples here. So for examples, you have degree of indeterminacy 2 here, degree of indeterminacy 2. So you can remove this and you can remove this. 2. Then you have a displacement here, displacement here. You can find this displacement first. Then you put by where you remove that one, and you can find byfbb dash and byfcc dash. Look at this flexibility coefficient, deflection at C due to the load at B. You can see that. Then second time you can do this cy, and you again find the displacements, that cy times displacement at B due to the load at C. Displacement at C due to load at C. Right, so this is superposition method, by the way. So if I superpose everything, by the way, this would be like this. It could be go like up this one, just cancel it, and it could be like this, and you can put by and cy up. So in that case, so if I superpose it, this is down, this is up, then it will become this one. So you can see superposition. You remove 1, you remove 2, then you put 1, then you put another one, superposition all 3 of them, then you will get these answers, right? So you have a 2 compatibility condition, extra 2 compatibility condition, that delta B here plus this equal to 0. This plus this equal to 0, and you can find those unknown quantities using this matrix. OK, for the beam, same thing, that if you have a more for I think what happens here? Oh, for this one, if you are, for examples, as I mentioned, displacement at I, this is flexibility coefficient, displacement at I due to the load at J. So that's what they talk about. Sometimes you can use the tables that I have given to you. For examples, if you want to find the displacement at any point, let's say someone asks you to find the displacement at point, so you can put x equal to, let's say, L by 2, and you can find the displacement, you can find the maximum rotation, you can find the maximum displacement. These tables will be useful when you do the calculations, right? Because sometimes you can use the ready equation for displacements, because ultimately in the force methods, our main goal is to find the displacement. So you can use these tables for some typical cases. For cantilever beams, for simply supported beam, there are some cases here. There are some cases here as well. Now let's take an examples. Let me solve this example for you. OK. Determining the reaction of the beam and draw shear force bending moment diagram, flexural flexibility coefficient. This is flexural rigidity. Sorry, flexural rigidity. Flexural rigidity. EI is equal to constant. Let me put my solution up here. All right. So step number 1. Step number 1, we're going to find degree of indeterminacy. How do we going to find degree of indeterminacy? I think there is an equations 3m plus r minus 3n. Number of members 1, 2, 2 members. Reaction force 3 reaction force, 1 reaction force. Number of joints 1 and 2. So 3 times 2 plus 4 minus 3 times 2 will give me 6 plus 4. I screwed up something there. All right, let me find that equations. 3m 3m plus r minus 3n. So why it's not working? So number of members, oh, there are only one members, sorry, one member, so 1, so 3 plus 4 minus 6, 7 minus 6, 1. Okay, sorry, that's just make corrections. Number of member is equal to 1. So there is only one members. All right, degree of indeterminacy is done. Seconds, we're going to draw the primary structures. Primary determinant structures. Determinant structures. Primary structures are always determined by removing one redundant force. Right? So how many redundant force you have? 1, 2, and 3, and this one. So let's remove this redundant force. So if I remove that redundant force, then this is my structures, right? You can have these structures, and your load is 50 kilonewton here. And when I remove this structure, then this becomes your point. Let's say this is point B, and this is point A. So let's find this delta B. So now to find the delta B, let's find the delta B. Let's find delta B. How are we going to find? Because as I mentioned, your main structure, real structure is like this. A and B, and you have 50 kilonewtons. And this is 6 meters and 6 meters. So these deflections would be like this. But in that case, when I, oh sorry, this would be like this. Then if I remove this one, then these displacements would become like this, right? So you have some additional displacement, that delta B, because when you remove these supports, you will get this displacement. So let's find these displacements using the virtual work methods. So our problems, forget about everything. Our problem is this one now. So to find the displacements using the virtual work methods, there is a simple methods that, okay, 0 to L, small m, capital M over EI dx. I think you remember these virtual work methods. This is virtual work methods. Virtual work methods, week number 7. Right? So let's use the virtual work methods. So this is a real structures. This is the virtual structure. So let's do the real structure first. Capital M we're going to find. Let's say this is 50 kilonewtons. This is A. This is B. 6 meters, 6 meters. Let's make a 2 cuts. Cut number 1, cut number 2. Let's make a cut number 1 from here to here. Let's say this is X1, and let's say this is X2. So first one, if I take the first cut, point B, cut number 1, capital M1, and that would be 0. If I take a second one, point B, 50 kilonewtons, and that is 6 meters. Cut number 2, let's say M2, and this is X2. In that case, sum of the moment at cut equal to 0, anti-clockwise positive, minus 50 kilonewtons times X2, and minus M2 equal to 0, M2 equal to minus 50 X2. Right, so two things done. Capital M1, capital M2 find. Now we need to find the virtual loads, right? Because we need to find the displacements, right? So in the virtual methods, you can remove that real one and you put the virtual load in the where you want to find the displacement, right? You want to find the displacement at point B, so you put the virtual load 1 where you want to find the displacements. And again, we're going to make the same cut. You remember the story that we can't change our style, that all the x1 coming from here, x2 coming from here would be same. Now let's do this. So here cut number 1, x1 and small m1. So sum of the moment at cut equal to 0, anti-clockwise positive. So you got all right, you got m cut, so you got minus 1 times x2 minus m2 equal to 0, m2 equal to minus x2. So that is 1, sorry. And then you can make a second cut, 6 meters. Actually the same thing. We can't make a difference between capital M1 and capital M2. So you got M2, sum of the moment at cut equal to 0, anti-clockwise is positive, minus 1, 6 plus x2 minus m2 equal to 0, m2 equal to minus 6 minus x2. Right, so we have everything to calculate deflection delta B equal to integrations 0 to L small m1 capital M1. So let's make it 0 to 6 over EI dx1 plus 0 to 6, or you can make it 6 to 12, 6 to 12 m2 capital M2 over EI dx2. I hope you understand that you have x1 starting from 0, finish at 6 meters, right? So 0 to 6 m1 capital M1 EI, and then this x2 start from 6, finish at 12. So 6 to 12 m2 capital M2 EI dx2. So let's plug the value. This will be immediately 0. Why? Because your M1 is capital M1 is 0. So if you plug capital M1 0, you get this 0. So you're dealing with only 1. So let's say 6 to 12. Capital M2 is minus 6 minus x2 times capital M2 minus 50 x2 minus 50 x2 over EI dx2, right? And then 1 over EI 6 to 12, expand this bracket, 300 x2 plus x2 square dx2, right? Then 1 over EI 6 to 12, 300 x2 square on 2 plus x2 cubed on 3. Uh, 50, 300, and that require 50 x2, right? So 50 times 6, 300 x2, then plus 50 x2 square. Right, now that looks better. 300 x2 square on 2 plus 50 x cubed on 3. Six to 12. So 1 over EI 300 times 12 square on 2 plus 50 times 12 cubed on 3 minus 300 times 6 square on 2 plus 50 times 6 cubed on 3. Right, so 1 over EI. Let me use my calculators. 21600 plus 28800 minus 5400 plus 3600. So I think I have done something wrong there. Let me fix it. Something 612 300 x2 square. How about we just take the 50 out? That makes it more simple. Then we are dealing with a small number, so let's take a 50 out. EI 6 to 12 x2 6x2 plus x2 square dx2. 50 over EI 6x2 square on 2, so which is 3x2 square plus x2 cube on 3, 6 to 12. $50 on EI 3 times 12 square plus 12 square on 3 minus 3 times 6 square minus, and that would be cubed. So 3 12 square 12 cubed on 3 minus 3 6 square minus 12 cubed on 3. So 3 times 12 times 12 plus 12 cubed on 3 minus 3 times 6 times 6 minus 12 cubed on 3. I think there is something wrong. That's I'm not figuring it out, but I think I will give you some other way to do it. So 6 cubed over 2 over. Yeah, so let's take an answers from my solution, that is 9,000. I think you know the integration. I just screwed up somewhere something. So 9,000 over EI, and that's displacement coming down. I think I can give you in the workshops where I get the wrongs, so you will have full pictures. So in the breaks I will find it out. So let's say delta B 9,000 over EI. Okay, there are some calculus that I screwed up something. All right, so now let's say you understand that, right? So you find deflection delta B here. Finding the deflection delta B, that's 50 kilonewtons. We remove the supports and we find the deflections. Now we follow the same, we take the same structures. Now let's say step number 4, we're going to calculate deflection at B due to unit load. Right, so now we will have You remember that we have this one, 50 kilonewtons, and we have roller supports here. We remove that roller. And then 50 kilonewtons. So we have this one, delta B. Now we want to put it back. So 50 kilonewton is not there. We just want to put this one by By, and then you will have this deflection delta BB, which is equal to flexibility coefficients times by By. Right. So now our intentions to find delta BB dash, which is flexibility coefficient of BB By. So let's find delta By. It's very simple there, that you want to have a By going up, and we need to find this deflection delta BB dash. Right. So deflection delta BB dash, we can use our lecture notes. You remember that I give you the table. Table is here. So let's take this cantilever. Again, you can use virtual work methods if you can't use these tables. Okay, so you can use virtual work methods to calculate if you can't use these tables. Now in these tables, you can see P is your By. So we need to find the maximum deflections because we need to find at this tip here. So we have P, which is your By. We have a length, which is 12 cubed over 3 EI. So 12 cubed give you 1728 By on EI 3. Divided by 3, you get 576 By on EI. Right, so that's simple. So now we have a compatibility conditions. Compatibility equations. What is compatibility equations? That delta BB, which delta BB going down, right? Delta BB going down, by the way. Yep, here we put it there, right? So delta BB going down, so let's put minus. Delta dash BB going up, so let's put that plus, and that equal to 0. Why? Because you understand that, right? That you have 50 kilonewton here, and when you remove this roller supports, you get delta BB. When you put this force back, you get this delta BB dash. But you want to have this roller support back, which has a delta B equal to 0. So that's this down equal to this up, or you can add them together equal to 0. Let's plug the value. Delta dash BB, which is 9,000 over EI minus 9,000 over EI plus delta BB dash 576 By on EI equal to 0. EI constant, so we can take it other side and multiply by 0. You get 9,000 plus 576 By. So By equal to 9,000 positive over 576. So 9,000 over 576, you get 15.625 kilonewtons, right? So this is job done now. Job done meaning that you have 50 kilonewtons here, and we find that By going up because it's positive, 15.625 kilonewtons, and you have 6 meters and you have 6 meters. And this is point A and point B. Now this structure is determinant because you have only 3 unknown value. Now we can draw the shear force and bending moment diagram using our conventional methods. What is the conventional methods? That we can draw free body diagram, AY AX MA 50 kilonewtons, 6 meters, 6 meters, and that point B has 15.625 kilonewtons. Now in this case, you can take a moment at point A equal to 0, anti-clockwise is positive. You done this one many times, right? 50 kilonewtons times 6 meters plus 15.625 kilonewtons times 12 meters and plus MA equal to 0. So this is minus 300 kilonewton meters. You got 187.5 kilonewton meters plus MA equal to 0. So MA equal to 112.5 kilonewtons meters. Now we can do some of the force in the y directions. Upward is positive, AY going up, 50 kilonewton going down, plus 15.625 kilonewtons going up. So AY equal to, you got 34.375 kilonewtons. AX equal to 0 because there is no horizontal force. So you got this 34.375, you got this 15.625, point A, point B, and the moment is 112.5 kilonewton meters. And you have 50 kilonewtons here. And that is 6 meters, and that is 6 meters. Now, in this case, we can just do the shear force diagram. SFD in kilonewtons, just graphical methods. 34,375 going up, going across. 50 here is 34.375. 34.375 take away 50, give you 15 point minus, by the way, 15.625. Match it up here. This is minus, this is plus. Right, and this is 15.625. Now bending moment diagram. Bending moment diagram, kilonewton meters. So the bending moment diagrams, you will get anti-clockwise negative, 112.5 kilonewton meters negative. Then this area. How much? Because this is 6 meters. So that would be 34,375 times 6. 34 times 375 times 6. You get 206.25. So positive 206.25. Take away 112. Take away 112.5. That is coming from here. So you got 93.75. So up to this point, you got 93.75 positive kilonewton meters. I think kilonewton meters, put it here. And this is the roller support, so that would be 0. Now you might need to find this distance x, the slope of the line, that you can find it by taking this 93.75 93.75 take away 112.5 over 0 take away 6. So 3.125 slope. slope 3.125 x 0, 3.125x minus 112.5. So this would be 0. 112.5 over 3125x. Sorry, something is, I just need to do it again. I think I screwed up something. I think you know how to find those linear line equations, and then from that you can find this x where y equal to 0. So you got the concept there, right? I can show you the space gas to match up these answers. Let me show you the space gas. Now for the space gas, we are working on these examples. Here you go. So we have a fixed supports, roller support, 6 meters, 6 meters. So let's turn off this. Draw member, press 0 in your keyboard, and then press 6 in your keyboard, and then press 6 keyboards again. Keep it horizontals. Escape key to get out from the commands. Double click on this one. We have these fixed supports and casters. We have a one single click or double click, and we have roller supports here. One click, 50 kilonewtons load minus y, 50 kilonewtons. Hit OK and OK and OK. So if you can't see that one, you can just put diagram annotations and hit OK. You can see you can put these fixed beam and rollers. Now we need to put those dummy material property. You can put any dummy one like a universal beam or just from this library. Universal beam. Let's 150 universal beam. Hit OK, and this whatever you put here, it will not going to affect. Let's put Young modulus for steel 200,000. This again not going to affect these properties for your answers. So analysis, we have everything. Linear static analysis. Hit OK. OK, that's finished. If you want to know if you want to put the wire, you can put the wire. And if you want to turn off this, so you can clearly see. If you want to first see reaction forces, 34, 15, 112.5. That's what we got, right? 112.5, 34, 15, 112.5. That is correct. Now, if you want to draw the shear force and bending moment diagram and you want to turn off this loading, that is the bending moment diagrams. So 112.5, 93.75. Upside down, you remember these concrete beam and steel beams. So 93.75, 112.5, and that is 0. You can, I think you cannot see this. All right, so that's good. Now, shear force diagrams, 34, 15. So 34 and 15. So you got everything there. I hope you understand that. And oh yeah, I agree. Last one should be 6 cube. Okay, so let's do that. 3 times 12 square plus 12 cubed divide by 3 minus 3 times 6 square minus 6 cubed over 3. You got 8. This answer is 828 times 50. Still, it's not working, but that's okay. Week 8 lecture example 2. Oh, here. So now is a degree of indeterminacy equal to 2. Now degree of indeterminacy equal to 2. How? Let me turn example showing you degree of indeterminacy equal to 2. Step number 1, we're going to determine degree of indeterminacy. All right. So in that case, we have a member 1, member 2, 2 members. How many reaction force? 3 reaction force, 1, 1. So total 5 reaction force. How many joints we got? 1 joint, second joint, third joint. So degree of indeterminacy is equal to 3m plus r minus 3n. So 3 times 2 plus 5 minus 3 times 3, 6 plus 5 minus 9. So 11 minus 9 give you 2. So that's the degree of indeterminacy equal to 2. Now number 2, we will going to make this as a redundant structures. So let's draw primary structures. So we can see these 2 rollers, we can remove it immediately and we make it cantilever. So these structures become like this. This is your primary structures because you need to remove 2 and that is 6 kilonewton per meter. And the total length is, let's say there is an additional point. Let's put the additional point A, B and C. There is a 6 meters here, 6 meters here. When I remove this one, then the structures become not, by the way, not like this. You have a horizontal line here. And then you just got this point. So you have a delta C here that we need to find. And we need to find this delta B. Right. And then we need to have a additional that going to put in the opposite direction. Let's put the opposite one. What is that? Let's put this BY up. And due to this BY at this particular point, you got BY deflection at B due to the load at B. And in here, C point, we have BY force deflection at C due to the load at B. So I hope you understand that. And there is another one. Oops, sorry, we can just. There is another one, A, B, and C. There is another one that we're going to apply CY here. For that CY, we have CY deflection at B due to the load at C. This one here, there is CY deflection at C due to the load at C. So I hope you understand that. Now compatibility conditions become delta B, which is down, minus plus this one up, by FBB and CY FBC equal to 0. I hope you understand that. Compatibility condition here at C, delta C minus delta C plus by FCB plus CY, sorry, CYFCC equal to 0. You can put it in the matrix format that delta B, delta C minus minus plus FBB, FBC, FCB, FCC, BY, CY equal to 0. Right? I hope you understand that, right? So there are how many quantities we need to find? Deflection 1, 2, 3, 4, 5, and 6. 6 deflections we need to find. It's quite a big job. Quite a big job, meaning that finding the deflection is quite tedious, right? It's one deflection require 1 page of work, and there are 6 pages of work. So as I mentioned, this finding degree of indeterminacy with 2 is quite challenging. Let's start working, because we need to find the deflection delta B first over here. Deflection delta B over here. So for that deflection delta B, we have equations that we can really use. I think this no, this is we need a cantilever. Oh, here you go, cantilever one. Let's get that equations. Copy. Let's get that equations delta B. We need to find the deflections here. Minus. Let's put minus because it's going down. Let's put minus going down. W. What would be the W here? 6. So let's put the 6 there. Over 24 EI. Distance we need to find at 3 meters. Is it 6 or 3? Let me check the questions. It's at 3 meters. So this is not 6. That is 3 meters and 3 meters. So in here we can put 3 to power 4. Take away 4. L is 6 times 3 cubed plus 6 square times 3 square. Right? So in that case, let me get this 3 to the power 4. Take away 4 times 6 times 3 to power 3 plus 6 times 6 square plus 3 square. Three to power 4, away 4 times 6 times 3 cube plus 6 times 6 times 6 times 3 square. Minus 624 EI 1377 times by 6 divided by 24. You got minus 344.25 over EI. Right, so I think first deflection is found. Deflection delta B. As I mentioned, we need to find 6 of them. So deflection delta B found. Now let's find deflection delta C. Deflection delta C, I think this is the maximum one. So it's WL to the power 4, 8 EI minus, because it's going down, so minus W is 6, length is 12, 8 EI minus 6 times 12 to the power 4 over 8. You got, oh sorry, Oh, that is 6 square. Just make a correction. 6 times 6 to power 4 over 8. You get 972 over EI. I hope you understand finding the deflection, second deflections. Third deflections that we need to find is this uh, this one here, FBB. That is, let's give them name delta dash BB, delta dash BC. Let's give them name delta let's give them 1 and delta dash BB2 and delta dash BC2 and 1. So let's say delta dash BB1 we need to find equal to. I think there is an equations again that we can use, or these equations we can use. Let's get this. All right, now the first one that we're going to use this by in the 3 meter distance. I think we can't use this one. Do we have? Let's use the. Yeah, okay, so here we can use this maximum deflection. I think they put the points here. That's maximum deflections here, by. So in that case, let's use this positive PL cubed on 3EI. So you got P load is what is by, right? We got by. So P load is by. L cubed is 3 because it's midpoint over 3EI. So you got 9 by on EI. That is going up. So that's done. And then we will have, let's find this another one. Let's find this one, this guy's here. Delta dash BC2. Delta dash BC2. That is exactly this one. So PL cubed again going up, so it's positive. P is CY. P is CY times L cubed is 6 square, 6 cubed on 3EI. So 6 to the power 3 over 3, you got 72 EI. Now there is a one simple rule that is, I think, let me find that another one as well. We found this ones. We found these ones. Let's find another one that is FBC. Let's find this one. Let's find this one. Delta dash BB2. Delta dash BB2. Now we can use the same one here. Because delta dash BB2 we got, I think at the midpoints we need to find for this one. So midpoint would be in these equations. We're going to substitute x equal to I think 3. So P 6 EI x cube minus 3LX square. So P is we are finding this one. So P is CY on 6 EI 3 cube minus 3 times 6 3 square. So 3 cubed minus 3 times 6 times 9, you get 135 over 6, 22.5, and that is positive, I believe. 2.5 over EI. Now there is a one simple what is that called? Bett's law. Let me find the name. Bett's law. Structure of analysis. What is Bett's law going to tell us? Yes, so that is the name. Bett's law. Now, what is Bett's law? So Bett's law is telling me that when you have a structure like this, you look at this by same structures, 3 meters, 3 meters, 3 meters, 3 meters, and this by and this cy. So this value, which is this one, should be equal to this one based on Bett's law, because you can see these displacements here by, these displacements here cy. Graphically, it's not showing because I did not draw by scales, but this force by, and if you have another force cy, then this displacement that is here, they are same. So delta b dash, delta b c, that would be same as this one, 22.5 on EI, right? That is based on Bett's law. Now we have everything. We have everything to solve. Let me get that equations for me. So the equations that we got is delta B, delta C, and these are minus, plus FBB, FBC, FCB. I think this is flexibility coefficients, FCC, and then BYCY equal to 0. Now let's plug the values. Delta B, we calculate delta B, 344.25 minus 344.25 minus this minus recognized by this minus. Okay, so I'm not crossing it up. And then EI and delta C is 972 minus again minus 972. Let's say put 1 over EI outside plus flexibility coefficient. Flexibility coefficient FBB. So FBB was, I think our FBB, let me go back and check my figures. FBB was here, so which is delta dash BB1. So that is 9 over EI, and BY is here, by the way. So 9, let me put EY outside. And then FBC, just we found this one, 22.5. And this FCB, we found 22.5. And FCC, we found FCC somewhere 72. So 72 BY CY equal to 0, 0. Now these are cancels. If you take the common and bring it on that side, you will get that commons. And if you do this inverse and matrix stuffs, I think you remember that matrix one, so you get 20.50, or you can do the simultaneous equations, and then CY equals to 7.07 kilonewtons. Now, once you find that reaction forces, you can because you can see that this is fixed. By is 20.57 kilonewtons, then you have 7.07 kilonewtons, 3 meters, 3 meters, and then you have these 6 kilonewtons per meters. Then you can find this reaction force is unknown, MA, AX, AY, right? You can do this conventional way because now you know those methods. So these methods that you have seen, that method is used only when you have degree of indeterminacy equal to degree of indeterminacy 2. If you have degree of indeterminacy 3, then this becomes quite complex by hand. Quite complex by hand in the sense that it's not possible. It's quite long. It's quite tedious, and even 2 get complicated. 2 is possible. You can see with this one, 2 is possible, but more than 2, I think it will not possible. For that case, like multi-story and large complex, we generally use the stiffness methods. We generally use the stiffness methods for I think we're going to teach you the stiffness methods. Stiffness methods are used for these kind of multi-story building frame, and where the degree of indeterminacy greater than 2. In the 11 week, we have a stiffness method, very powerful methods that we'll leave it at the end. But slope deflection methods also useful. Get more insights. So let me go back to my lecture notes and I walk you through that last examples. So we solve all this one. Now, let me just go through this one. So determining the force in the member AC. So we need to find the force in the member AC either in the tension or in the compressions. So we need to find that force in the member truss shown in the figure. Take EA, axial rigidity equal to constants. Now, so let's find the degree of indeterminacy. You remember that equation, degree of indeterminacy equal to, let me remind you that degree of indeterminacy equations. Here you go, m plus r minus 2n. M plus r minus 2n. How many members you got? 1, 2, 3, 4, 5, and 6 members. So 6 members. How many reaction force? I think 1, 2, and 3. 3 reaction force. How many joints? Joint 1, joint 2, joint 3, and joint 4. So 9 minus 8, degree of indeterminacy equal to 1. So first step, always you find the degree of indeterminacy for the beam and for the truss. Now, for primary structure, since the axial force in the member AC need to be determined, so we need to find the force in the member AC, right? We need to find the force in the member AC. So there is a one unknown force that would be not reaction force, but you have this axial force is chosen to be redundant. So we need to find this force that we're going to choose it redundant. OK, we're going to remove that force that we assume that is not there and we're going to put it back. Therefore, the primary truss created by cutting the member AC. So we just say that this member is not there. We just cut it. Why I choose this one? Because that's the force we want to find it. OK. Like in the beam, we make the reaction force redundant. Here in the truss, we make this axial force members that is made. If it is 2 redundant, then you need to make it 2 members to be gone. OK, to be removed. Just make a cut there. So let's say I make this cut and make this structure primary structure. Now this is primary structure. By the way, let's say this force is this is not there. So if this member is not there, your primary structures would look like this, like this, and again you need to make it stable, by the way. So that is, and this would be 2 kilonewtons, right? So I think that's pretty much it. You need to find this. So when you remove that force, then this has a displacements in these directions, right? Because these truss are these members, if there, then this displacement. So there is a displacement in that one. So you have delta AC that you're going to find using the principle of virtual work in the week number, I think week number 7. Just make a corrections here. So delta AC, I think this is due to the virtual load. This is due to the real load, length, and this one. So you find this. Because you have 2 kilonewtons, you can find the reaction force, you find all the internal axial force, joint methods, and you can find this capital N. And then you put the virtual load 1, and then you find the small n, right? So you have two trusses. One is the real, remove that one, and you have 1 kilonewtons going in the direction where you want to find the displacements, and you find the small n, and you substitute that value. You find that displacement delta AC 16.8. I hope you understand that. It's like same concept in the beam that we have done. Once you find the displacement, then you come back here and you put back this force FAC, right? You remember that we put that force back in this one. This force is there, so we put it back, and we again find the displacement or flexibility coefficients AAC, and we find the displacement again because this is 1, by the way. We don't know this force FAC, so it's 1, and this is virtual 1 is 1, so you have n square, so you have 10.37. And from that, these displacements that you have calculate, and this displacement that you have calculated, this is negative, and this is plus. You can make it 0, and then you can find the FACC. By the way, it's just finding 4 displacements for I think 1 displacement, and then there is a second displacement, 2 displacements equal and opposite, and then you can find the unknown forces. So in the summary, first of all, you need to find the degree of indeterminacy for the beam and truss. D equal to 3m plus r minus 3n. That is the beam equations. That is the truss equations. Once you find the degree of indeterminacy either 1 or 2, I think in these examples we generally give you 1 or 2. It will not gonna go more than that. Once you find that, you draw the primary structures and find the displacements. You know how to find the displacement, so find the displacements, and then you put this force back where you find the displacements, and you find the displacement in opposite direction. Of course, you remove all the real loading in this second primary structures, and then you make it 2 equals, that is compatibility conditions, delta B down, delta BB dash up, down negative, this one up positive, and you are able to find the unknown force, unknown redundant force. Once you find the unknown redundant force, you are able to analyze this beam like a conventional way using the equilibrium equation, and you can draw the shear force and bending moment diagrams. For truss, again, you can find the degree of indeterminacy, and then you remove one member, just completely remove and find the displacement in that directions using the virtual work methods. You put that force back, and you again find a displacement like a flexibility coefficients, and then you make it both equal. You get able to find the unknown forces. This methods has a limitations. Degree of indeterminacy 1, user friendly. Degree of indeterminacy 2, little bit complex. Degree of indeterminacy 3, it will be quite challenging. So in that case, I suggest there are other methods that we're going to teach you, but these methods particularly used to analyze the indeterminate structures, truss and beams and frames. Frames is not in our course, but you can also analyze the frame using these methods. So any questions? I think I screwed up few steps here. I think the one thing that I will correct it is this, that in my next in my workshop examples, I will, after this one, I will check what I done wrong and give you some more insight on that one. Yeah, and in the workshops, we're going to talk more examples and some space case softwares as well. Any questions or any comments?